Today we're going to be working on balancing chemical equations. But first, I want to talk about several elements that kind of behave a little oddly. And these have a tendency to, instead of just being alone, so let's say something like tin. Tin metal by itself is just Sn. But these elements exist as diatomic molecules. So if I say, for instance, hydrogen, let's say hydrogen, let me write this down here. If I say hydrogen reacts with oxygen, okay, when we write the chemical formula, instead of writing H plus O, we have to use the molecular formulas, okay? So this is H2 plus O2. And these are very, very common compounds, right? These elements pop up a lot in chemistry. So it's important to remember that these things exist as diatomic molecules. Now, the thing that people kind of get confused at after I say this is, let's say that I say something like sodium bromide. All right, so people seem to think, well, okay, so I have bromine, so that's Br2. Well, no, this is an ionic compound, okay? So this is NaBr because I know that bromide has a charge of -1 and sodium has a charge of +1, and I only need 1 to balance the charge, okay? You only use these as diatomic molecules if they're by themselves, not part of a compound, just by themselves. All right? Now, I am going to ask you to remember these, and there's kind of an easy way to remember them. There are 1, 2, 3, 4, 5, 6, 7 of them. Okay? There are 7 of them, and they make the shape 1, 2, 3, 4, 5, 6. Okay? So this right here, this little bit right here, makes the shape of a 7. Okay? Let me see if I can... no, that's not going to work. So these three, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Okay, there we go. Those make the shape of a 7, but we also add in hydrogen. Here's the other one, okay? So it's these ones and hydrogen, but they mostly make the shape of a 7. So you just remember the shape of the 7, and you have to remember that hydrogen is also in there, okay? So that's for starters. Now, a lot of times you'll see something as a word equation, okay? And we need to be able to go from word equations to formula equations, all right? So a formula equation uses the chemical formulas, but being able to convert between the two of them is, as you'll see, quite important, all right? So here we go. Here's our word equation. We have our reactants, we have our products, we have methane and oxygen reacting to form carbon dioxide and water, okay? So I could write this as methane, which is CH4. You don't know that one, but I would give it to you, plus oxygen. Now remember that oxygen is one of those funny diatomics. Reacts to form carbon dioxide plus water. Okay? So if I look at this, I have some problems, all right? So why don't you pause, look at this formula equation, and tell me if you can figure out what the problem is. If you look at this, I have 4 atoms of hydrogen on this side. Let's say that this is kind of single molecule scale. I have 4 atoms of hydrogen on this side, but I only have 2 atoms of hydrogen on this side, which means that I have destroyed 2 atoms of hydrogen. And on this side, I have 2 atoms of oxygen, and on this side I have 3 atoms of oxygen, which means that I have created 1 atom of oxygen. That all to me makes me a little frowny face with maybe a little tear here because I'm sad. And why am I sad? Conservation of mass and conservation of matter. Okay? Matter cannot be created or destroyed, neither can mass. They're really very equivalent concepts. So what we say is that this is what's called an unbalanced chemical equation. And what we do when we balance equations is we go through and we make sure that the number of atoms on each side are the same. Okay? All right. Now, there aren't like rules for balancing an equation. They're always going to be a little bit different, all right? Because there's so many different iterations of these. So what I have here is I have a couple tips, all right? These are things that I think can help you balance equations quickly, all right? Now, at a certain point, this is expected to be kind of second nature to you, and you should be able to do this very quickly. When you're first getting started, we're going to go slow, and I'm going to expect this to be a little difficult, all right? But you'll get plenty of practice. All right, so here's my example. CH4 plus O2 yields CO2 plus H2O. Should look familiar, right? So here are my tips. One, look for even-odd disagreement and fix it. Well, what do I mean by that? Let's take a look at the oxygens, okay? I have 2 oxygens on this side, and I have 3 oxygens on this side. And there is nothing that I could multiply this by in order to make that the number of oxygen atoms on this side odd, which means that I'm going to have to fix this to make it even, all right? So I'm going to put a 2 here, and I'm going to know that this number always has to be a multiple of 2. So that's important to keep in mind. So when I do that, okay, I get 4 oxygens, which means I'll have to do this. And then I'll look at the hydrogens, so that's 2 hydrogens per water molecule times 2 water molecules, so that's 4. And this has 4, so that's good. And there's 1 carbon here and 1 carbon here. Perfect, okay? So this one, this look for odd-even disagreement and fix it, that's usually a good place to start. Sometimes, though, it won't be. So here are a couple more. Put a coefficient of 1 in front of the most complex molecule, and then hope. Okay, and then just hope it works. Because there will be times when we'll be doing some crazy stuff, and you're hoping that the complex molecule has a 1, because if it doesn't, life's going to get tough. All right? Now this one's pretty good. Balance atoms that only appear once per side first. Now we kind of violated that because of the odd-even disagreement, but the odd-even disagreements, that's good stuff, okay? But this one is also good. If there's no odd-even disagreement, balance something that only appears once per side. And then there's a 4th one, and this one's pretty good too, all right? If there's a polyatomic ion that is unchanged, so let's say maybe on the reactant side you have potassium sulfate, and on the other side you have calcium sulfate. Well, the sulfate ion didn't actually change, okay? So treat this as one quote-unquote thing. All right, so rather than balancing the sulfur and the oxygens, I can say I'm going to balance this sulfate ion and I'm going to balance this sulfate ion. Now, if I went from like potassium sulfate to like sulfur dioxide plus oxygen plus some other stuff, okay, now I wouldn't do that because my sulfate got broken up. All right, you understand the difference there? Now, here, this is important. No fractions in the final answer. I'm telling you right now, there will be a time this year where I will tell you to put fractions in, but I will be very clear and say you will use fractions now. Okay? I'm going to show you an example in a minute where you'll use fractions. All right? But not yet. Do not put fractions in the final answer. Because if we're talking about this stuff on a single molecule scale, like it wouldn't make sense to say, I want half of a molecule of oxygen. That just doesn't make any sense at all. Okay? So these are all things that you can use to balance chemical equations. Okay? These are all tips that you can use. So now we're just going to have a whole bunch of examples.